Welcome to our lesson on determinants. A determinant is a special number that can be calculated from a square matrix. Let's learn how to find determinants for both 2 by 2 and 3 by 3 matrices. Let's start with a 2 by 2 matrix. Here's a simple 2 by 2 matrix, A. To find its determinant, we use this formula, multiply A times D, then subtract B times C. Let's try an example. Here's our matrix. To find its determinant, we'll multiply 4 times 9, which is 36, and subtract 2 times 6, which is 12. So the determinant is 36 minus 12, which equals 24. Now, let's look at 3 by 3 determinants. For a 3 by 3 matrix, the process is a bit more complex. We'll use what's called the Saris rule or the rule of Saris. The rule of Saris tells us to add 3 products going down to the right and subtract 3 products going down to the left. Here's the formula. AEI plus BFG plus CDH minus SEG minus D minus F. Let's solve an example. Here's our 3 by 3 matrix. Let's find its determinant using Saris rule. First, let's calculate the positive terms. 2 times 4 times 1 equals 8. 1 times 2 times 1 equals 2. 3 times 0 times 2 equals 0. Adding these up, 8 plus 2 plus 0 equals 10. Now, for the negative terms. 3 times 4 times 1 equals 12. 1 times 2 times 1 equals 2. 2 times 0 times 2 equals 0. Adding these up, negative 12 minus 2 minus 0 equals negative 14. Finally, we add the positive and negative terms together. 10 plus negative 14 equals negative 4. Therefore, the determinant of our matrix is negative 4. And that's how we calculate determinants. Remember, for 2 by 2 matrices, multiply diagonally and subtract. For 3 by 3 matrices, use Saris rule to add the products going right and subtract the products going left. Welcome! Today we'll learn about minors, cofactors, and their role in finding determinants of matrices. Let's break this down step by step. Let's start with a 3 by 3 matrix as our example. Here's our matrix A with elements a 1, 1, a 1, 2, and so on. First, let's understand what a minor is. A minor of an element is the determinant of the matrix that remains after removing the row and column containing that element. Let's find the minor of a 1, 1. To calculate this minor, we find the determinant of the remaining 2 by 2 matrix. That's a 2, 2 times a 3, 3 minus a 2, 3 times a 3, 2. Now, let's learn about cofactors. A cofactor is the minor multiplied by negative 1 raised to the sum of the row and column numbers. For position I, j the cofactor is minus 1 raised to I plus j times the minor. Let's work through a complete example with actual numbers. Here's a 3 by 3 matrix. Let's find the minor M11. We remove row 1 and column 1, leaving us with this 2 by 2 matrix. The determinant is negative 1 times 1 minus 4 times 2 equals negative 9. Now for the cofactor C11, we multiply the minor by negative 1 raised to 1 plus 1, which is 1. So C11 equals negative 9. If we continue this process for all elements, we get the complete matrix of cofactors. Finally, we can use these cofactors to find the determinant of the original matrix. The determinant equals the sum of each element in any row or column multiplied by its cofactor. This is called expansion along a row or column. Let's expand along the first row. That's 2 times negative 9, plus 1 times negative 22, plus 3 times negative 10. The determinant equals negative 18 minus 22 minus 30, which equals negative 70. And that's how we use minors and cofactors to find determinants. Remember, first find the minor by calculating the determinant of the remaining matrix, then multiply by negative 1 raised to I plus j to get the cofactor, and finally use these to expand along any row or column to find the determinant. Welcome! Today we'll learn about Cramer's rule, a powerful method for solving systems of linear equations. Cramer's rule uses determinants to find the values of variables in a system of equations. Let's look at an example. Consider the system of equations. 2x plus 3y equals 8 and 4x minus y equals 1. To use Cramer's rule, we first need to write our system in matrix form. The coefficients of x and y form our coefficient matrix A, and the constants form our solution vector B. Let's first calculate the determinant of our coefficient matrix A. For a 2 by 2 matrix, the determinant is calculated by multiplying the diagonal elements and subtracting the product of the off-diagonal elements. Now, to find x using Cramer's rule, we replace the first column of the coefficient matrix with the solution vector and divide that determinant by the determinant of A. Let's call this new determinant d underscore x. According to Cramer's rule, x equals d underscore x divided by the determinant of A. So x equals negative 11 divided by negative 14, which equals 11/14. Similarly for y, we replace the second column of the coefficient matrix with the solution vector and calculate that determinant. Let's call this new determinant d underscore y. Then, y equals d underscore y divided by the determinant of A. So y equals negative 30 divided by negative 14, which equals 15/7. Let's verify our solution by plugging these values back into our original equations. In the first equation, 2 times 11/14 plus 3 times 15/7 equals 8. And in the second equation, 4 times 11/14 minus 15/7 equals 1. To summarize Cramer's rule, first, calculate the determinant of the coefficient matrix. Then, for each variable, replace the corresponding column with the solution vector and calculate that determinant. Finally, divide these new determinants by the original determinant to find the value of each variable. Cramer's rule is particularly useful when dealing with 2 by 2 or 3 by 3 systems of equations, providing a systematic way to find solutions using determinants. Calculate the area of a triangle using a 3 by 3 determinant. The formula states that the area of a triangle equals 1/2 times the absolute value of the determinant of a special 3 by 3 matrix containing the coordinates of the triangle's vertices. Let's start with a simple example. Consider a triangle with vertices at points A, 0, 0, B, 4, 0, and C, 2, 3. Let's plot these points on a coordinate plane. To find the area, we'll set up our determinant. We'll create a 3 by 3 matrix where each row contains the x-coordinate, y-coordinate, and 1 for each vertex. Now we can expand this determinant using the first row. Let's solve each 2 by 2 determinant. The first 2 terms are 0, so we only need to calculate the last determinant. That's 4 times 3 minus 0 times 2, which equals 12. Remember to take the absolute value and multiply by 1/2. Therefore, the area of our triangle is 6 square units. Let's try another example. This time, let's find the area of a triangle with vertices at A-1, 2, B3, 1, and C2, 4. Setting up our determinant, we get this 3 by 3 matrix. Let's expand along the first row again. Calculating each 2 by 2 determinant, we get negative 1 times negative 3, minus 2 times 1, plus 1 times 10. This equals 3 minus 2 plus 10, which equals 11. Taking the absolute value and multiplying by 1/2, we find that the area of this triangle is 5.5 square units. This method of using determinants to find triangle area is particularly useful when working with coordinates in the coordinate plane. Remember the key steps. First, set up the 3 by 3 determinant using the coordinates. Then, calculate the determinant. Finally, take the absolute value and multiply by 1/2 to find the area. A quadrilateral using determinants. This is a powerful method that works for any quadrilateral, even irregular ones. Let's start with an example. Consider a quadrilateral with vertices at the points A1, 1, B4, 2, C5, 5, and D2, 4. Let's plot these points and connect them to form our quadrilateral. To find the area using determinants, we'll use a special formula. The area equals 1/2 times the absolute value of a determinant. We'll arrange our coordinates in a special way. First, write all x-coordinates, then write all y-coordinates, and finally repeat the first point's coordinates at the end. Now, let's calculate this determinant. We multiply diagonally from left to right and add these products. Then we subtract the products of diagonals going from right to left. Let's work it out step by step. Simplifying this, we get 44 minus 36, which equals 8. Therefore, the area of our quadrilateral is 1/2 times 8, which equals 4 square units. This method works for any quadrilateral, regardless of its shape. It's especially useful for irregular quadrilaterals where traditional formulas might be difficult to apply. The determinant method gives us the exact area without having to break the shape into triangles or use other geometric approaches. Remember, the key steps are: first, write your coordinates in order, repeating the first point at the end. Then use the determinant formula, and finally multiply by 1/2 to get your area. With practice, this method becomes a powerful tool for finding areas of complex quadrilaterals. Welcome! Today we'll learn about determining the consistency of a system of linear equations using determinants. A system of equations is consistent if it has at least one solution and inconsistent if it has no solutions. Let's start with a simple example. Consider the system of equations: 2x plus 3, y equals 6, and 4x plus 6, y equals 12. To determine if this system is consistent, we'll use determinants. We can write this system in matrix form. The coefficient matrix A contains the coefficients of x and y, and matrix B contains the constants. To check consistency, we'll calculate two determinants: the determinant of the coefficient matrix A and the determinant of the augmented matrix AB. Let's calculate the determinant of matrix of first. For a 2 by 2 matrix, we multiply the elements on the main diagonal and subtract the product of the other diagonal. So A equals 2 times 6 minus 3 times 4. This gives us 12 minus 12, which equals 0. When the determinant of the coefficient matrix is 0, this means the equations are linearly dependent. In other words, one equation is a multiple of the other. Let's verify this. If we divide the second equation by 2, we get the first equation. This means these lines are actually the same line. Let's visualize this geometrically. When we plot these equations, here's the line 2x plus 3y equals 6. And when we plot 4x plus 6y equals 12, we get exactly the same line. This means the system has infinitely many solutions. Every point on this line is a solution. Let's look at another example. Consider the system: 2x plus 3, y equals 6, and 4x plus 6, y equals 15. Let's check if this system is consistent. Let's write this in matrix form and calculate the determinants. The determinant of A is still 0 because we have the same coefficient matrix. Now let's check the determinant of the augmented matrix, AB, when A equals 0. But AB is not equal to 0. The system is inconsistent. It has no solutions. Let's visualize this. Here's the line 2x plus 3, y equals 6. And here's the line 4x plus 6, y equals 15. Notice that these lines are parallel. They never intersect. This means there are no points that satisfy both equations simultaneously. Let's summarize the consistency conditions using determinants. If A is not equal to 0, the system has a unique solution. If A equals 0 and AB equals 0, the system has infinitely many solutions. If A equals 0 and AB is not equal to 0, the system has no solutions.